So today we're going to look at solving an ordinary differential equation. We have x squared times y prime is equal to x squared plus x times y plus y squared. And what we're going to look at is one of the common ways to solve differential equations of this category, as well as this type of differential equation in the way that it's classified. So to begin with, we can look at what we are given here. And we can recognize this as a first order differential equation. We know that it's first order because the sort of biggest derivative that I have is a first derivative, and that's this y prime term right here that I circled in green. And the second thing that I need to do before I can make an attempt at finding a general solution for this thing is to determine what particular type of differential equation that I'm working with. Now, this is likely not going to be a linear differential equation because I've got this y squared term. It's likely not exact. It doesn't look like it. It's likely not separable to begin with because we have this funny x times y term right here. And so if I do anything to try to separate that out, then since I have a single x term by itself, I'm going to have to apply a y variable to it. It's not going to be easy to separate. So really what I'm stuck doing is looking whether or not I have a homogeneous differential equation or an inhomogeneous differential equation. And one of the things we need to recall is that a differential equation, ordinary differential equation, is inhomogeneous if there are any terms separated by a plus or a minus which do not include the dependent variable, which is this y as a function of x. So we normally don't include this y of x in the shorthand here, but we do like to view the dependent variable like it is a function of the independent variable y of x. So notice here that I have these two terms that contain the dependent variable y, but I do have one term here at the beginning on the right-hand side that does not contain the dependent variable. As a result, this is an inhomogeneous differential equation. If all of them had included the dependent variable, then we would have a homogeneous differential equation. So a differential equation is inhomogeneous if there's any term separated by a plus or a minus that does not include the dependent variable. So this is inhomogeneous, and as a result, we need to use some kind of trickery, a special type of substitution here to turn this into something that's maybe a little bit easier to deal with, and then we'll use like some separation of variables or other techniques if it happens to work out that way based off of that substitution that'll make our life a little bit easier. So the common substitution here is sometimes written a number of different ways. We choose a dummy variable like u or v, and I think t is another one that gets used sometimes if you're familiar with your second year calculus. And what we want to do is choose that dummy variable u or v is equal to y over x. And I don't like writing it this way because I find that sometimes when I'm going on a bunch of problems like this, I start to get tired, and then I make little algebra mistakes when I'm like reorganizing the sides. So what I do instead is I notice that if v is equal to y over x, well then y is equal to v times x. And then what I need to do is I need to go ahead and figure out what the y prime term is, and we're viewing y prime like it's dy over dx. So dy over dx is just going to be the derivative of this thing, because the derivative of y is dy dx. And then the derivative of v with respect to x and the derivative of x with respect to x, we're going to have to use a product rule in order to put together what dy dx is equal to. So the product rule says that I'm going to take the first term v, I'm going to write it down, times the derivative of the second term, which happens to be x, and the derivative of x is just 1. Then I'm going to add it to the derivative of the first term, which is dv with respect to x, so dv dx, times the second term, which is x. So now that I have these two nice expressions for what y is equal to and what dy dx is equal to, I can substitute this into my original expression, and then we can start doing some algebra to make this a little bit easier. So first of all, I have x squared here into dy dx, which is this v plus dv dx x term is equal to x squared does not change under our substitution, plus x does not change under our substitution, but we know that y is v times x under our substitution. So I'll have x times vx plus, and then y is vx under our substitution squared. Okay. So now what I need to do is maybe clean this up a little bit. And of course we would like to get the dv dx term by itself, because what we're going to see here is when this cleans up nicely, then we have some like separation of variables that we can do, which will allow us to use those sorts of techniques to find the solution. So I'm going to start by dividing everything by this x squared term, in which case we'll notice that we can cancel the x squared off of the left-hand side, simply leaving us with v plus dv over dx times x is equal to x squared divided by x squared gives us 1 plus, here I have x into vx, so that's going to be vx squared divided by x squared, which is just v. And then I'm going to have v squared x squared over x squared, which is just v squared. And you can see that this turns into something rather easy to handle at this point. So now what I'm going to do is I'm going to try to isolate my dv and my dx term to get ready for the final solution here. Before I integrate, I need to get the v terms all on one side. I can do that by subtracting v from both sides, and I should probably keep the colors the same here. So that'll leave me with dv over dx is equal to, and that should be x dv over dx, is equal to 1 plus v squared on the right-hand side. Okay, so the next step here is going to be to figure out how to get the x and the dx on the same side and the v and the dv on the same side. And of course we could very easily just like divide off this dv term, which will give us x over dx. And maybe I should say that I'm being a little bit cavalier here with like dividing off the differential part. It's not exactly accurate, but most of the time in differential equations we can sort of work this way and it will work out reasonably well for us. There's very few cases where that distinction is actually going to matter. So I'm being a little cavalier with what I'm saying here, but you know, it works in this particular case. So if we divide off the dv term, then we get something that looks like this. Well, we notice that we can take a reciprocal of both sides, because if this thing is equal to this thing, then the reciprocal of this thing is equal to the reciprocal of that thing. And we can also just do this with some like basic algebra. You know, if you wanted to multiply off the dx to this side and then divide off the x, you get 1 over here, and you multiply the dv and you divide off the 1 plus v squared. You can see that it's very easy to just do the reciprocal of this thing. So we get dx over x here is equal to, and then next we have dv over 1 plus v squared over here. And now I have a nice, easy expression which I can proceed to integrate at this point. Okay, so in order, now that I've separated out my variables, I can take this dx over x and this dv over 1 plus v squared, and I can integrate on both sides. Now dx over x, of course, is just the natural log of the absolute value of x, and I'm going to include this constant term here. And on the right-hand side, notice that I have this dv over 1 plus v squared. Well, that's like 1 over 1 plus v squared, which is the same thing as the arctangent derivative. So this is the arctangent of v Okay, but we noticed that we made a substitution originally, and that is that y was equal to v times x. So v is equal to y over x. So as I go through my final general solution here, I'll get the ln absolute value of x plus c is equal to the arc tangent of, and then I replace with what my substitution was originally. I'll have y over x here on the inside of arc tangent. And then of course it can be noted that what we're going to do at this point is maybe try to solve for one thing or the other, just depending on what is required of your class. And maybe I want to collect the constants over on the right hand side. And since that's just arbitrary, I can just move the plus c from one side to the other. There's no issues with that whatsoever. Okay, so as you can see, the substitution y is equal to vx can reduce an inhomogeneous differential equation to a nice algebraic form in which we can eventually convert this thing into a separable differential equation. And these are always very simple because we just integrate both sides once we've separated out the variables. All right.